In this video, we're going to talk about mechanical vibrations, a mass going back and forth on a spring. This kind of motion is sometimes called harmonic motion and is incredibly important throughout physics with a wide range of different types of applications. So what's the idea? I want to imagine I have a mass m. It's sitting on some surface, which at least at the beginning I'm going to presume is a frictionless surface. Maybe it's ice, or maybe there's really nice frictionless wheels on the block, something like that. And it's attached to a spring. So if at the beginning this is at rest, for example, I'll put an equilibrium position to say if I don't touch anything, that would just sort of rest right here. But if I grab it, I could move it away from that equilibrium spot. And then the question is, well, what happens if I let go? Because it's a spring, the spring is going to want to return it to the equilibrium position, but it can't do it directly. It's going to sort of go off and overshoot and end up on the left side of that equilibrium position. And then you can imagine it would spring back and it would cross back over and back and forth it would go. So how do we model this? How do I write down equations that represent this? How do I solve those equations? So we're going to begin with just a little bit of analysis of the forces that are involved, because we have Newton's second law that tells us that the sum of the forces is equal to the mass times the acceleration. And it's going to be convenient for us to write acceleration as just the second derivative of the displacement x. Now, the only force that's relevant, because I'm assuming it's frictionless at the beginning, is what we call Hooke's law. And Hooke's law gives us the force of the spring acting on the mass. And the idea is it's negative k times x, where k is just some constant. And then x here, I've represented as the displacement, but specifically it's the displacement from the equilibrium. So I have this one vertical line here, which was where the spring would like to be at rest. And if I move away from that, I get a displacement of x from x equal to 0 being that equilibrium position. That's the x that we're measuring specifically in Hooke's law. And it's negative because if your x was to the right, if it was a positive value of x, the force would push it back to the left. It would push it back towards the equilibrium point. So there's always that negative. And then the k, the spring constant, well, it depends on the properties of the spring. If you've got really thick coil, then you might have a larger value of k. A really light, sort of flimsy spring would have a small value of k. So I have the generic Newton's law for forces being mass times acceleration. I have Hooke's law, and I'm going to compare those two things. I'm going to say thus that mx double prime plus, because I moved the force to the other side, plus kx is equal to 0. And that is my differential equation to describe this mass on a spring. So now this just turns into a problem of solving differential equations. We know what to do here. I'm going to guess a solution of the form x is equal to e to the rt for some unknown r. I get the characteristic equation because two derivatives of e to the rt gives me an r squared. So mr squared minus k, cancel the e to the rt's, it's equal to 0. And then this I can solve. This is r is equal to plus or minus I times square root of k over m. Only thing that I'm going to do that's new here is, I sometimes like to relabel this. Square root k over m, it comes up a lot. Sometimes this is relabeled as omega naught. Omega naught here just stands for, basically, the frequency is, I'll show you in a little moment. So it's just a shorthand for root k over m. Okay, so what was the next step in our process to solve a differential equation like this? Well, e to the plus or minus I omega naught, we saw could be converted into sines and cosines. There's no real part to our r's, so there's no exponentials. And the imaginary part by Euler's formula gets converted to cosine and sine, so I get a cosine omega naught t plus b sine omega naught t. And it's in this context that it makes sense to call omega naught a frequency. It's cosine omega naught t, and thus I get the frequency of omega naught. Bigger values of omega naught means my sine and cosine terms oscillate faster. So this solution that I have to the mass on the spring problem is perfectly fine. And it does make sense from the perspective of oscillations. Cosine and sine are both oscillating terms, and we were expecting our mass on the spring to go back and forth and to oscillate. But there's one other standard little trick that we do here, because having a cos and a sine is a little bit annoying. So I want to combine them. I'm going to see whether it's possible for me to write it in a new way, which is with only one trigonometric term, cosine. So I can have a new coefficient c out the front. And then I'm going to have the omega naught t, but then minus a gamma. So I haven't showed you how to do this. I'm going to see, can I do it? Well, we have a trig identity to deal with cosine of one thing minus another thing. So I could expand that guess and write it as the constant c out the front, then cosine of omega naught times cosine of gamma, and then plus sine of omega naught times sine of gamma. And so if I compare this to the original, well, for example, there's a cosine of omega naught t in both two places, but I get these relationships that A then would be c times cosine of gamma and B would be c times sine of gamma. And now it's just a question of solving for everything. So, for example, I could solve for the c just by Pythagoras. It would be square root of a squared plus b squared. And I could solve for the gamma because the tangent of gamma would be equal to b over a. And then you could take an arctan from there. And so the final point is that this solution of the form a number c times cosine of omega naught t minus gamma is really the solution to the frictionless mass on the spring. Let's check out what this looks like graphically. To help me graph this, I've come and put in this function of the form a cosine wt minus g. I have to use Roman numerals, not Greek ones, for this particular software. And what I'm really interested in is how does the shape of this curve change as I change the different parameters? And first of all, we see this sort of oscillatory behavior, and that is corresponding to, if I think of y as my position, this mass on the spring going back and forth, and it's oscillating, so that at least makes sense. The coefficient a out the front here is represented by amplitude, and I can grab this slider and change it. And if I make a bigger value of a, I get a bigger amplitude, and if I make a smaller value of a, I get a smaller amplitude. So as you change the value of a, it's like, how far back and forth is this oscillating? If you do a tiny tweak to your system, it might just go back and forth a little bit. If you do a really big tweak, it might have a really big amplitude. The next one I'm going to change is the w, which we called omega naught earlier. So if I take this w slider and change it around, as I increase it, there's faster and faster oscillations. And if I decrease it, then things get spread out a little bit more. So this is all related to, is it going back and forth quickly, or is it going back and forth slowly? And indeed, this depends on omega naught, which is the root k over m. It's going to depend on properties of the mass and the spring constant. A bigger mass, for example, is going to mean slower oscillations. And then finally, we have to deal with this shift. It's not omega t, but when we convert it, we have this omega t minus gamma or g here. And if I take this, watch what happens. This represents the shift. This is just going to shift basically where the starting location is. It moves it to the left or the right. And that sort of motivates this type of trigonometry because it's saying, look, all we're doing when we have a cosine term and a sine term is basically just have a cosine term but shifted a little bit. And this is the degree of that particular shift. So that's how the three different parameters affect the shape of the graph. All right, so what we've done was entirely the frictionless case. In the next video, I'm going to talk about how to deal with mechanical vibrations when we include friction as well.